385 light years from here, there is a dot. It's faint. It's orange. It sits in the corner of an image that took 20 years of engineering to make. And according to every model we have for how planets are built, that dot cannot be there. Webb photographed it anyway. So what is it? Because here's the part nobody tells you. That single image wasn't the discovery. It was the door. What came through that door in the 3 years afterward is a chain of findings that shook exoplanet science down to its foundations. A world that may be wrapped in an ocean, a molecule that made 100 scientists stop breathing, and then a public collapse of that same finding that almost nobody covered. By the end of this video, you'll understand exactly why a growing number of astronomers now say, we are not looking for life anymore. We are looking for a way to prove we found it. And right now, those are two completely different problems. Before we go in, if you want the version of this story that survives contact with the actual data, not the headline, subscribe. This channel is where that version drops first. To understand what Webb did, you have to understand why it took us this long. We've known about planets around other stars since the 1990s, thousands of them. But almost every single one was found indirectly. We never saw them. We saw their shadow, a star dimming a fraction of a percent as something crossed in front of it. Or we saw their pull, a star wobbling, tugged by an unseen mass. Real astronomy, real discoveries. But you were never looking at a planet. You were looking at a graph. Photographing one directly is a different category of hard. Imagine standing 5 miles away from a lighthouse at full power. Now find the firefly hovering next to the lamp. That's the problem. A star can be 1 billion times brighter than the planet beside it. The glare doesn't just outshine the planet. It floods the detector, it scatters inside the optics, it drowns the signal in noise before the light even reaches the sensor. There were direct images before Webb. A handful, blurry, hard-won, argued over for years. But Webb was built with something different. Coronagraphs, physical masks that sit inside the instrument and block the star's light before it can contaminate anything else, combined with a 6.5-meter mirror and infrared eyes cold enough to see heat that faint. And here's the detail almost every video gets wrong, and it matters for everything that follows. Webb didn't photograph reflected sunlight bouncing off a planet. It photographed the planet's own heat. Young, giant planets are still glowing from the violence of their own formation. Hundreds of degrees, sometimes over 1,000. In infrared, they don't reflect. They burn. Which means Webb's very first target had to be young and massive and far from its star. It found one. September 2022. The image goes public. HIP 65426b. A gas giant somewhere in the range of 6 to 12 times the mass of Jupiter, orbiting a young star about 385 light years away. That's not the strange part. The strange part is where it sits. It orbits roughly 90 times farther from its star than Earth does from the Sun, 3 times Neptune's distance. Out in the frozen outer dark, where, according to standard formation theory, there shouldn't have been enough material to build anything that big. Because here's how we think planets form. A young star spins inside a flat disk of gas and dust. Grains stick together. Pebbles become boulders. Boulders become cores. A big enough core grabs gas and runs away with it, and you get a Jupiter. That process needs density. It needs the material packed close and moving fast. Out where HIP 65426b sits, the disk would have been thin, sparse, spread across an unimaginable volume. Building a 7-Jupiter planet out there, by slow accretion, would take longer than the stars existed. The star is only about 14 million years old. Do the math, and you get an object that appears to have arrived before it should have been possible to make it. But that's not even the strangest part. So how did it get there? There are 3 serious ideas on the table, and I want to be clear about which is fact and which is hypothesis. All 3 of these are hypotheses. Nobody can say for certain which is right. 1, it didn't grow. It collapsed. Instead of building up grain by grain, a chunk of the disk became gravitationally unstable and fell in on itself directly, forming a giant planet fast, more like a failed star than a grown planet. 2, it formed closer in, where the material was rich and was then thrown outward, flung by a gravitational encounter with another massive body we may never find. 3, and this is the one researchers tend to bring up quietly. It never belonged to this star at all. It formed alone in interstellar space, wandering, unattached, and was later captured. Some astronomers use a phrase for objects like that. Orphan giants. Worlds that lost one family and were adopted by another. And if that's what happened even occasionally, then the galaxy is full of free-floating giant planets drifting between stars, occasionally getting caught into orbits that make no sense to us. Which raises the question that reframes this whole video. If we don't actually understand how planets arrive, what else are we assuming? Hold that thought. Because about 6 minutes from now, that assumption is going to break something much bigger. Now, Webb can only directly image a few dozen worlds this way. Big, young, far out. For everything else, the small planets, the interesting planets, the ones that might actually matter, Webb uses a different trick entirely: transmission spectroscopy. And when a planet passes in front of its star, a sliver of starlight filters through its atmosphere on the way to us, and every molecule in that atmosphere eats specific wavelengths of light. Water leaves one fingerprint, methane another, carbon dioxide another. So the light arrives here, carrying a chemical readout of an atmosphere trillions of kilometers away. We are not guessing at these worlds anymore. We are reading them. And in 2023, Webb read one that stopped the field cold. K2-18b, about 124 light years away, roughly 8.5 times Earth's mass, orbiting inside the habitable zone of a small red star. Webb found methane. Webb found carbon dioxide. That combination, in that place, fit a hypothesis called a Hycean world, a global liquid water ocean sitting beneath a thick hydrogen atmosphere. Not Earth, not Neptune. Something in between that we had never confirmed existed. And then, buried in the same data, a faint signal at a wavelength that made everyone stop. Dimethyl sulfide, DMS. On Earth, DMS is produced almost entirely by life. Marine plankton, ocean algae, it's part of the smell of the sea. Nobody claimed proof. The original team was explicit that it was tentative, but it was there, and it was in the right place, on a temperate world with methane, carbon dioxide, and a possible ocean. And then things got worse. April 2025, new data. This time from Webb's mid-infrared instrument, MIRI, at wavelengths, the first observations never covered. The Cambridge-led team reported features consistent with DMS and possibly dimethyl disulfide at what's called 3 sigma. 3 sigma means roughly a 0.3% chance the data would look like that by fluke. The team said it plainly. Either we're seeing signs of life or we're seeing a chemical process producing DMS without life that we don't yet understand. For about 72 hours, it was the biggest story on Earth. And here's where it stops making sense. Because in astronomy, 3 sigma is not a discovery. The standard for a claim like this is 5 sigma, roughly a 1 in 3 million chance of a fluke. 3 sigma is a flag. It's look again. The graveyard of physics is full of 3 sigma results that evaporated, and this one started evaporating almost immediately. Independent teams went back to the same public data with their own pipelines, not to attack anyone. That's how the system is supposed to work. What they found is genuinely unsettling, but not in the way you'd expect. One reanalysis confirmed methane at about 4 sigma, solidly, but found no statistically significant evidence for carbon dioxide or DMS at all. Another group ran the numbers across dozens of different data reductions and hundreds of atmospheric models. Their conclusion? The DMS signal was extremely sensitive to arbitrary choices made during processing. Change a defensible assumption, and the molecule disappears. Another team examined the mid-infrared data specifically and found it highly vulnerable to instrument systematics. Depending on how you group the wavelengths into bins, a routine, boring, technical decision, you get wildly different atmospheres. Under their preferred binning, the vast majority of their runs showed no biosignature. Their assessment was blunt. What's in that mid-infrared data is likely correlated noise, not a planet. And a joint analysis combining all 3 instruments across the full spectrum found the evidence for DMS or DMDS insufficient, and found that several other molecules with a similar chemical structure fit the data just as well. A separate reassessment put the DMS signal at around 2.7 sigma, close to the original number, still nowhere near enough. There's one more detail that quietly removed the foundation from underneath the whole thing. DMS was detected on a comet, 67P, no life involved, and in the interstellar medium too, which means the core premise that DMS on a planet implies biology is no longer safe. It's not even the strongest version of the argument anymore. By late 2025, the position across most of the field was that the biosignature claim had been examined thoroughly and had not survived. So was the whole thing a failure? No. And this is the part I want you to actually take away. Because in between all of this, Webb did something that nobody argued about. WASP-39b, a puffed-up gas giant orbiting so close to its star that its atmosphere is roasted to over 800 degrees Celsius. Webb read it: water, sodium, potassium, carbon monoxide, carbon dioxide, the first clear, unambiguous detection of CO2 in an exoplanet atmosphere. And then something nobody had ever seen anywhere: sulfur dioxide. Here's why that mattered. Sulfur dioxide can't just sit in that atmosphere. It has to be made continuously by high-energy starlight breaking molecules apart and forcing them into new combinations. That's photochemistry, the same class of process that builds Earth's ozone layer. Until that moment, photochemistry on another world was theory, equations, simulations. Webb caught it happening. That single result proved the method works. It proved we can detect a molecule that exists only because a specific ongoing chemical process is running right now on a planet we will never visit. Which means the failure at K218b was never a failure of the telescope. It was a failure of certainty. And there's a difference, but that raises a harder question. If Webb can nail sulfur dioxide on a furnace, why can't it settle a small, cool, temperate world? The answer is the twist this whole video has been walking toward. Look at the pattern. Proxima b, the closest potentially habitable planet to Earth, 4 light years, and we cannot properly characterize its atmosphere because it sits far too close to a star that dominates everything we see. And that star, Proxima Centauri, is a red dwarf that flares violently, blasts of radiation that can strip an atmosphere over geological time. It's plausible Proxima b has no atmosphere left. Plausible, not proven. Nobody can say for certain. TRAPPIST-1. 7 Earth-sized worlds for years, the crown jewel. The Webb checked the 2 innermost planets. TRAPPIST-1b, no thick atmosphere. TRAPPIST-1c, no thick carbon dioxide atmosphere. Bare rock, cooked by an ultra-cool dwarf. And K218b, also orbiting a small active star. Do you see it? Every single one of our best targets orbits a small red star. That's not a coincidence. It's a bias built into the method. Small stars make small planets easier to detect, so that's where we look. But small stars are loud. They have star spots. They flare. They vary between one observation and the next. And here's the thing that broke the field's confidence. A star's own surface features can imprint a fake atmosphere onto your data. If a planet crosses a cool spot on the star, the light you collect carries the spot's chemical fingerprint, and it can look exactly like a molecule in a planet's sky. That's called stellar contamination. And when researchers looked hard at TRAPPIST-1e, they found evidence of it in every single one of their observations. So the real obstacle was never distance. It was never mirror size. It's that we've been trying to read a whisper while standing inside the noise that's making it. Which brings us to the one planet still standing. And to a solution so simple, it's almost embarrassing. TRAPPIST, atom 1. E, roughly Earth-sized, sitting in the habitable zone, arguably the single best rocky planet target we have. In September 2025, 2 papers reported the first results from 4 Webb transits. The findings, stated carefully, there is no thick primordial hydrogen atmosphere. That's ruled out. Venus-like and Mars-like scenarios are disfavored. Hydrogen-rich atmospheres with methane and carbon dioxide are excluded. But the data does not lean strongly for or against an atmosphere overall. 2 scenarios remain live: a bare rock or a secondary nitrogen-rich atmosphere, possibly with traces of carbon dioxide and methane. A nitrogen atmosphere with trace gases. That is a description of Earth. It's also a description of nothing at all. And with 4 transits contaminated by a restless star, we cannot tell which. So here's what they're doing about it. They're using TRAPPIST-1b, the innermost planet, the one Webb already showed is almost certainly bare rock, as a control. It crosses nearly the same track across the star's face, so any feature that shows up in both spectra can't be coming from a planet's atmosphere. It has to be the star. Subtract it. What's left is TRAPPIST-1, E's actual sky. 15 more transits are underway. Roughly 130 hours of Webb time pointed at one system. That's the answer to the dot we opened with. Not a discovery, a method. Webb's first image proved we could isolate a planet from its star's glare in one dimension. This does it in another, and when those observations are complete, they could deliver the first definitive detection, or definitive non-detection, of an atmosphere on an Earth-sized world. But that raises a terrifying new question. What if the answer is no? Because run the pattern forward. Every rocky world we can currently examine in detail orbits a small, angry star. If small stars strip their planets bare, and so far the evidence keeps leaning that way, then the entire population of worlds we're able to study might be the population least likely to hold anything. Meaning the silence we're hearing may not be the universe's silence at all. It may be the sound of us searching in the only place our instruments let us look. That's speculation. I want to label it clearly. Nobody has proven it. But it's the reason the next generation of telescope concepts are being designed around one specific capability: physically blocking starlight with enough precision to see an Earth beside a sun-like star. Because there is a real possibility that the answer to the oldest question we've ever asked is sitting in front of a star we can't currently point at. And there's something else worth sitting with. That collapse at K218b, the reanalyses, the arguments, the retraction of confidence, that was the system working. Publicly. Painfully. In front of everyone, a claim was made. The data was released. Strangers took it apart. It didn't hold. That's not a scandal. That's the only reason you'll be able to believe it when something finally does hold. And when it does, when a signal survives every team, every pipeline, every hostile reanalysis, and still stands at 5 sigma, You'll know it's real because you watched what happened to the one that wasn't. We started with a dot that shouldn't exist, 385 light years away. We still don't know how it got there. Formed fast, thrown out, or captured from the dark. Nobody can say for certain. But that image bought us something bigger than an answer. It bought us the ability to separate a world from the light that hides it. And right now, Webb is spending 130 hours doing exactly that to a planet the size of ours. If this shook you, hit subscribe and turn on the bell. Because when those 15 transits come back, we're covering the result the same day, at this depth, with the caveats intact. And if you want to understand why so many rocky planets around red dwarfs end up airless, the flares, the stripping, the reason the closest world to Earth may be a dead rock, watch that one next. The dot is still out there. We're just finally learning how to look at it.